Hello, ladies and gentlemen. What we have here is not one of our lectures, but kind of an off the cuff video that I wanted to make for you guys. I was thinking about what I wanted to put on the test, and I think that these topics that we've been covering of fluids and waves tend to be a lot more abstract. They feel a lot more abstract to students. They tend to be a lot more difficult, and so I don't want to make the final have questions from only these topics, because I think that then we'll be looking at a final that feels extremely difficult, and that's not what I want here. So what I was thinking is I'd like to have the final have a couple of problems that I would generally intend for you guys to use conservation of energy to solve. Okay, and it might be possible to solve them in other ways, but in general, conservation of mechanical energy should be kind of our favorite tool because it's our easiest tool to use. Okay, and so I don't have slides made up for this or anything like that, like I usually do for a lecture. I just have paint here, and I just wanted to do just kind of a review, a refresher, a little additional video to help you guys better understand how to use conservation of mechanical energy. Okay? So remember that conservation of mechanical energy was our equation UI plus KI plus work non-conservative equals UF plus KF. Okay? Now, what I want this video to be about is specifically how to use this, okay? So, when we go to use conservation of mechanical energy, what we do is we write down this equation, okay? There's a reason I make you guys write down the general equation, and so that I can look at this, and then what I do is I look at each term in turn, and I think, okay, is there any of that in this problem? And if so, what is it? Okay? So, when we use this, let's look at a problem from the last test. Okay, remember I gave you guys the one where Jim Bob was going to take a running leap off a cliff. So Jim Bob runs up, right, and he jumps like this. And I didn't tell you theta, okay, and I told you v naught. Now the reason I didn't tell you theta is because I didn't want you to use kinematics on this, and I hoped that you would think that it would be too much of a pain to solve with kinematics if you didn't know theta. Now, it is actually solvable without knowing theta, but it's a pain, okay? It is actually solvable with kinematics without knowing theta, but it's a pain. But it's very easily solved with conservation of mechanical energy, okay? So I'm going to use that as an example here, and then let's just look at how we use conservation of mechanical energy, okay? Conservation of ME, mechanical energy. So what I do is I decide that I'm going to use this, and I have to pick an initial time and a final time, right? There's initial on this side, on the left side, and there's final over here on the right. So I have to pick an initial and a final. Initial, I'm going to pick right when he leaves here, okay? And initial and final, there's nothing special about them. They could be any times, but generally we need to pick them at times that we're going to know something about the system, okay? So the easiest is this one, right at the start when he leaves, I know V naught. So I'm going to use that as initial, okay? And then he was jumping in the water down here, so he's going to fly out and he's going to hit the water. And the question was, what was his speed when he hits the water, right? VF equals what? So then I'm going to pick the final as right when he hits the water, okay? And then the cliff has a height of h. Okay? So I know at my initial time, right here when he leaves the cliff, right up here, that he's some height h above the ground, above the water, and I know that he's moving it with a speed v naught, and it doesn't actually matter what direction the speed is in. Okay? And then I know when he hits the water, he's going to have some speed v final. Okay? And then I know at that point, all this h is gone, right? His height is 0. Okay? And by 0, I'm already picking a coordinate system, right? I'm choosing the water to be 0. Okay? So then let's look at how we use this. The first thing I say is when I look at on the left, I'm only looking at my initial position, okay? I only care about initial right now. So I look only at initial and I say, okay, is there any potential energy? Okay, U is potential energy. Now in this class, I only taught you two potential energies, right? I taught you MGH, that's gravitational potential energy, okay? And I taught you 1/2 kx squared. And that's the potential energy that's stored in a spring, or something that we can kind of approximate as a spring, right? Where x is the displacement from equilibrium. So if we have a spring that's normally this long, and then we compress it down some distance x, so now it's this long, this distance x is going to dictate energy that's stored in the spring, right? K is a property of the spring. It's like the stiffness of the spring, okay? So because I only told you two potential energies, that all you have to ask for this is for U initial, in this initial position, this first spot that I care about, is there any potential energy? Is there one of these two? All right. The answer is yes. There's gravitational energy because he's some height above what I'm going to call 0. Okay? So then I say yes, there is gravitational potential energy. Now, are there any springs or any spring-like things in this problem? There are not, right? So that I don't have this potential energy, okay? So let's get rid of this too. And let's write our solution down here, okay? So for U, we said that we have gravitational potential energy. That is there. There are no springs there, okay? So he doesn't have that, so I just write mgh, okay? And notice I'm just adding all of these energies, okay? So that's it. There are two kinds of potential energy that I taught you guys. Only one of them applies to this initial position, so I just write that one down, okay? And then I look at kinetic energy, okay? This next term, and I say, okay, are there any kinetic energies at this initial point, okay? And again, I taught you guys two kinds of kinetic energy, right? The first is 1/2 mv squared. And this is the kinetic energy of something kind of flying through space, kind of the center of mass of the object is moving, okay? So then the other kind that I taught you guys was 1/2 I omega squared, and this was the energy of something that is spinning, okay? And those are the only two kinds of kinetic energies that I taught you. So all I have to ask is at this initial point, do I have kinetic energy? Are things moving? The answer is yes, right? Jim Bob is moving. Okay, is Jim Bob spinning? No, Jim Bob is not spinning, okay? So this one is gone. And then I ask, okay, is Jim Bob's center of mass moving, right? Is Jim Bob's center of mass kind of flying through space here? Yes, it is, right? That's the whole point. He has this V0, his center of mass is moving. He's throwing his center of mass off the cliff, okay? So I add 1/2 mv squared. And it's always 1/2 mv squared. In this case, it's V0, right? That's the initial velocity that he has. And it's always 1/2 mv squared. That's the definition of kinetic energy, okay? And for the rotational piece, it's always 1/2 I omega squared. That's the definition of rotational kinetic energy, okay? For the potential energy, if it's gravitational potential energy, it's always mgh, okay? And if it's spring potential energy, it's always 1/2 kx squared, okay? I don't have to adjust these things for the problem, okay? I just have to decide which ones are appropriate, and I just write them into the problem, okay? Now this one is the hardest piece of the whole thing, the work non-conservative. So I have to ask myself for this one, are there any forces that are non-conservative forces in this problem? And what that means is, are there any forces that are changing the internal energy of objects or that are taking mechanical energy out of the system? Okay? Now, those kinds of forces are things like friction and air drag, okay? And I don't have those in this because I'm not considering those, all right? My approximation is that there is no air drag. And obviously he's flying through the air. There's nothing for him to rub against for the kind of friction that we've looked at for like blocks sliding down ramps and things like that. So I'm not concerned with that either, okay? So by the approximations of this problem, there is no non-conservative work being done, okay? So that one's just a 0. I don't need to write anything. I can move on to the right side. So then for the right side, I consider the final position, okay? And the final position that I've deemed, okay, what final is just the last piece that I care about, okay? So the last piece that I care about is right when he hits the water, okay? So right when he hits the water, I ask, are there any potential energies? Okay, so is there anything that's acting like a spring in this problem? No, there's not, okay? At this point, he hasn't stored any energy in any spring-like object as the final, okay? Now, gravitational potential energy is mgh. So there is mgh, but then what is h at v final? I've decided that at the beginning, his gravitational energy was mgh, where this is h, right? So that's his height above the point that I've deemed 0 potential energy. Okay, that's the way that always works. This h is always the height above whatever point you've deemed to be 0 gravitational potential energy, or below. Okay, we can pick a point here to be 0, and then he's, say, 1/2 h above at the beginning and 1/2 h below at the end, or something like that. Okay, but we didn't. We picked the water as 0 because that makes a lot of sense. Then we can just put the height of the cliff in the beginning. So at the end, his height is 0. And so he has no more gravitational potential energy. Okay, he's at the point that we've deemed to be 0 gravitational potential energy. Okay, so that's my two kinds that I know, right? And I've done them both, and now I move on. There's no potential energy for me to write down at the end. And then I look at the kinetic. So the kinetic, is Bob spinning at the end? Presumably not. Okay, there's nothing in the problem that should make us think that he is spinning. Okay, so there's no rotational kinetic energy. Then the 1/2 mv squared. Does Bob have kinetic energy of his center of mass moving through space? Okay, he does, right? Jim Bob is flying through the air. He has some v final at the end here, some probably pretty big v final, right? So yes, Bob is moving, right? His center of mass is moving. So he has kinetic energy, 1/2 mvf squared, right? And it's always 1/2 mv squared, right? Where m is whatever mass is moving, and v is whatever speed the object is moving at, okay? And then at this point, I've gone through each of these terms, right? I've painstakingly gone through each one of these terms, which is the way you do it. You do painstakingly, okay? Very carefully go through each one of these terms. I've written down the pieces that make sense for each one of these terms. So now I'm done with that piece, right? And now I've set up the problem. And at this point, I look at it and I say, okay, I always know G, right? H was given to me in the problem. V naught was given to me in the problem. M is going to cancel because it's everywhere, right? And VF is what I'm trying to find. So I have one equation. I have one thing that I don't know. It's the thing that I'm trying to find. So all I actually have to do now is algebra, right? And like we just said, the m's all cancel. I can multiply both sides by 2 to get rid of the half on this side, and I have VF squared equals, and then I have 2GH plus, and then 2 times the half is just 1, right? So then plus V naught squared. And so then VF equals 2GH plus V naught squared in a root, okay? And that was how I solved that problem with conservation of mechanical energy. Now, I made it really long by talking a lot at each step, right? At each term in this general equation up here. But in reality, it doesn't take very long, right? I just look at each one and I consider in each case, I just have for each U and each K, I just have 2 things that I've taught you guys, okay? So you just have to think, are either of those 2 things there? And then you move on. Are either of those 2 things there? Okay? And that's it. That's how we use conservation of mechanical energy. It should be our easiest and quickest tool to solve problems with. Okay? So now let's look at the other problem that I gave you guys for the test, which was the cart on the table, right? The other kind of clear mechanical energy one, or the main one that I'm thinking of. I think the last test maybe had 3 that could be solved with conservation of mechanical energy. But I had the cart, I had a pulley, and then I had a mass hanging from the cart, right? And then the question on the test was, how fast is this object going when it hits the floor, right? And I gave you kind of the radius of this pulley. I said that this pulley was hollow. I gave you the radius of the wheels, and I said that the wheels were solid discs, right? I gave you the mass of the cart that included the wheels, okay? So let's solve this thing using conservation of mechanical energy, just real slow and careful, just like we did the other one, okay? So C of ME says UI plus KI plus work non-conservative equals UF plus KF, okay? And this is problem 4 on test number 3, okay, if you don't remember. So, when we looked at this one, all we have to do is, again, look at each term in this general equation right here and write down anything that makes sense, okay? So, let's go ahead and do that. And what am I going to do for initial and final? That's my first decision, right? There's a left and a right. So what's initial and what's final? Initial, I'm going to take to be that point in time right before everything starts moving. Okay? That's going to be initial. Because at that point, it's done kind of being interacted with from the outside. I'm done interacting with it. It's just going to work on basic physical principles at that point, right? And then the final, I'm going to take to be when this block hits the ground. Okay? Because those are the 2 points that I care about and that I know a bunch of stuff about the system. Okay? So let's do that. So that point right before everything starts moving, I ask myself, is there any potential energy at the beginning? And remember, we know 2 kinds. We know gravitational potential energy, and we know spring potential energy. Okay? So, is there any spring potential energy in this problem? There is not, right? There are no springs. There's nothing that's going to act like a spring. There's nothing like that in here, okay? So this one is gone. And then at initial, before everything starts moving, are there any gravitational potential energies? There are, right? So this thing is some height h above the ground. That was given in the problem, okay? So if we call this guy little m, and the mass of the cart, including the wheels, big M, then we have little m GH is potential energy of the block that's hanging, right? Now I could also write big M G, and then let's call it D, I guess, where D is from the wheels to the ground, okay? So you see D and H aren't the same, right? And we wouldn't expect them to be because this block is hanging from a pulley. But I'm going to write big M, G, and D. Now, the pulley, I could say, has gravitational potential energy too, right? If the mass of the pulley, MP, is up there, it has MP, G, and then some other distance, D2, okay, above the ground, right? So I can write for each of these things, right? But then when I go to do U final, if we look ahead, the height of this thing hasn't changed, right? Of the cart hasn't changed, and the height of the pulley hasn't changed. So when I go to do U final, I'm going to have these terms again, right? This big M, G times D, and this mass of the pulley, G times D2. They're going to show up again in the final, right? And with the same sign, which means that they're just going to cancel, right? Because I can subtract it from both sides without changing the equation, okay? And this one is going to cancel because it's just going to show up on both sides. So in the end, when I think about this gravitational potential energy, I can consider only things that I know that their height is going to change during the course of this event. Okay? Now, if I'm not sure whether I can include something, I can just include it now while I'm doing initial, and then include it again when I do final. Okay? And the math will then work out, right? They'll just cancel. But if I see that something has a height that's not going to change, I can go ahead and leave it out when I do the initial and leave it out when I do the final, because I know that it's just going to have the same height both times and the terms are just going to cancel, okay? It has gravitational potential energy, but that potential energy never changes, right? It never gets converted to any other kind of potential energy. So it doesn't have any effect on the problem, okay? It's just kind of this thing sitting on the sideline doing nothing, okay? So for that reason, I'm going to skip these other two terms, okay? The one for the cart and the one for the pulley. If you're solving the problem, you could include them. You just have to remember to include them in the final as well, because they're still there, okay? So that's our potential energy in the initial, right? When it looks like this. The only difference at the end is that both things are moving and the block is down on the ground, right? This block here is down on the ground, okay? So, okay, we have potential energy initial, and all we've written down is the block, the gravitational potential energy of that, because it's the only thing that's going to move. It's the only thing that's going to have a potential energy that changes, okay? And then do we have kinetic energy initial? So at this moment in time, right before everything starts moving, is anything spinning? The answer is no, right? And then also, so that, let me go back one. Let's go even a little slower on this. The kinetic energy, remember we had the two types, 1/2 mv squared and 1/2 I omega squared. Okay? So at this moment of time, and I'm kind of giving away the cow here, before everything starts moving, do we have kinetic energy? Is anything spinning? No, it is not, right? And does anything have a center of mass that's moving through space? Also no, right? Because by definition, I've picked as initial that point in time right before everything starts moving, okay? So there is no kinetic energy. Okay, and then we come to this work non-conservative term. When we get to this work non-conservative term, we ask ourselves, are there any kind of friction forces that we're going to take into account? Is there any air drag that we're going to take into account? And in this case, the answer was no, okay? The problem actually just says basically that everything spins with no friction and there's no air drag and all that, okay? So we don't have any non-conservative work, okay? Now, if this was a block sliding on a ramp and we wanted to account for friction, then we would have non-conservative work, okay? And then we'd have to remember that work equals F dot D, okay? So if it was the force of friction, we'd have a friction force, okay? Maybe we'd replace this with the force of kinetic friction, right? Okay? But we don't in this problem, okay? So that's another 0. So now we're done with the initial. In the initial piece, all we have is this potential energy of the block, okay? And that's fine. We don't have to have a bunch of stuff. That's all that's important to this problem. What this problem is all about is the potential energy of this block getting converted to all kinds of kinetic energies, okay? That's all this problem is really about, okay? So we have potential energy of the block, and then we come to the end and we say, do we have any potential energies, okay? Now we talked about there is potential energy in the cart, right? And that was mg, and we called this distance d, right? But it didn't change. So we had it, if we wanted to include it, we had to include it in the beginning, and now we would have to include it again in the end, okay? And that's fine. We can include it that way, but we didn't. And if we wanted to include the mass of the pulley as potential energy, right? That mass times g times its height above the ground. We could do that, but we'd also have to include it at the end, okay? And it would cancel. So we didn't do that. So then the only object that's left is the block. And the final that we're concerned with is that moment right when the block hits the floor, okay? So right as the block gets to the floor, it's at a height of 0, okay? So there's no more gravitational potential energy. So our MGH term is 0 at the end, okay? And then our other potential energy that we know, 1/2 kx squared. Are there any kind of spring-like objects in this problem? The answer is no, right? At the end, there's still no spring-like objects being involved, so there's no spring potential energy, okay? So our potential energy at the end is 0, okay? So far, so good. We've gone through each term, and we only had to write down one thing, okay? So far, so good. The problem is really easy. But now we get to the end, okay? And this thing, the kinetic energy at the end, is there kinetic energy? Yeah, there's a kinetic energy all over the place in this problem, right? Okay, so let's start going through them one by one. Remember, we have two kinds that we know. 1/2 mv squared, that's movement of the center of mass of an object, okay, an object moving through space. And we have 1/2 I omega squared. And that is kinetic energy of spinning, okay? So let's start with the 1/2 mv squared. Are there objects whose center of masses are moving through moving through space, okay? And the answer is yes. There's two. First off, the block is moving, right? And so it has a 1/2 m vf squared, okay? And then the second thing is the cart is also going to be moving, right? So at the end, when the block is moving, the cart is moving, and they're connected by a string. And remember, when we have things connected by a string like this, they have to be moving with the same speed, okay? Now the cart has all these different parts, but all of those parts are moving together, right? The cart doesn't change shape or anything like that. So all the parts are moving together with this speed Vf, okay? All the center of mass of all the different parts is moving with this speed Vf, and we were given the mass of the cart as a whole. So the translational kinetic energy of the cart then is just 1/2 the mass of the total cart with the wheels and everything, m Vf squared, okay? And that's it. And so then we ask, okay, are there any other things where we have kind of the center of mass moving through space, this translational kinetic energy? And the answer is no, right? Those are the only two things that are kind of moving in that way, moving in some like direction that we can draw like this, okay? So that term is done. We wrote down all the sources of that. But now we move on to spinning kinetic energy. Do we have things that are spinning? Okay, and the answer is yes, right? For the wheels to roll, they have to spin about their center. So the wheels are spinning. And for the wheels, I have 1/2 I, and I'm going to put a W for wheel, okay, omega, and that omega is specific to the wheel as well, okay, squared, because I always have 1/2 I omega squared when something is spinning, okay? That's the definition of this spinning kinetic energy. Now, in this case, I have to ask, well, how many wheels do I have that are spinning? I have 4, okay? So I'm going to multiply this whole thing by 4. Now, I could just write this term 4 times, but that takes up a bunch of space, right? But I have to account for each object that's spinning, just like I accounted for each object that was moving through space when I wrote these two, okay? So I have 4 wheels that are all spinning, right? And then I have the pulley that's spinning, right? And so then I have plus 1/2 I of the pulley omega of the pulley squared, okay? And then is anything else spinning? No, right? Those are all the things that are spinning. Okay, so now at this point, I have to change these things up a little bit to work in the things that I know, okay? The MGH stays the same. The 1/2 m Vf squared stays the same. The 1/2 big M Vf squared stays the same. And then plus 4, well, let's just let's bring the half out, okay? So 4 times 1/2 is 2, right? So 2 times, and let me stop for a second and make this really clear. At this point, we've done the conservation of mechanical energy, right? We've done all of these terms, okay? And we've come up with an equation that describes conservation of mechanical energy for this specific problem, right? And now what I'm going to do is go through and modify this equation, manipulate this equation, so that I can eventually express the thing that I want to know, VF, in terms of things that I know, okay? So I'm going through here. I don't need to change any of these first terms, okay? And then the wheels, I said they were a solid disc, and I gave a mass for them, right? And it was some mass. I don't remember what it was. And I gave a radius for the wheels, right? So 1/2 m wheel r squared. And this half comes from the fact that it's a solid disc. And this mr squared is just kind of what moments of inertia always look like, okay? And remember, I gave you guys a table that had moments of inertia for all kinds of different shapes, okay? And a disc is just a cylinder that's spinning that has a really tiny height, right? Okay. And then the last piece that we kind of needed to know for this problem was rolling without slipping. When we roll without slipping, we kind of something spins and it lays out its circumference on the ground as it goes perfectly. Okay, so when I've laid out this much circumference, okay, if this is 5 centimeters, I've moved 5 centimeters on the ground. Okay, and for this to happen, we have to have a relationship where omega, the angular velocity, is equal to the translational velocity. Okay, if this is v of the center of mass, the translational velocity divided by the radius of the thing spinning. Okay? That's by definition for rolling without slipping. And the wheels are presumed in this problem to be rolling without slipping. Okay? So then, for each of these omegas, I replace it with the speed of the center of mass. Of course, the wheels have to have the same center of mass as the cart and everything else, right? Divided by the radius of the wheels, okay? Oh, this squared shouldn't be in here, okay? Omega is just v over r, and then omega was squared, right? So this whole fraction is squared. And then plus 1/2, and then the I for the pulley. Remember, the pulley was hollow, okay? Let me move this to give myself some space. So plus 1/2, and then the hollow pulley is going to have mass of the pulley times the radius of the pulley squared, okay? And then the omega for that one. So rolling pulleys, pulleys are involved in rolling without slipping, okay? That's the way that a pulley works, is the rope goes over the pulley. It doesn't slide over the pulley spins, and so it's effectively rolling without slipping. And the velocity is the velocity of the rope going over the pulley. And so the velocity of the rope, in this case the string, it's going to have to be the same as the block, right? Because the string doesn't stretch or anything like that. So the velocity that it goes over, it's going to have to be the same as the block to kind of keep up with the block. So we have another VF on top for our rolling without slipping, okay? And then we have the radius of the pulley on the bottom, okay? And so then we have all these different things, but now we have a bunch of stuff that we know, okay? We were given this mass of the block. We were given the mass of the cart and the wheels together. We were given the mass of each wheel. We were given the mass of the pulley. We were given the radius of each wheel. We were given the radius of the pulley, okay? And all we want to do now is solve for the thing we want to know, VF, okay? And you can see that I'll have, if I multiplied the whole thing by 2, there's halves on each of these things, right? And this one, the half and the 2 are going to cancel, right? And so what I'm going to end up with is a 2 mgh equals, and then I'm going to have VF squared. Notice that every single term has a VF squared, so I can pull it out. And then it's times. And then this one is going to be an M plus a big M plus, after I multiplied the whole thing by 2, I'll have a 2 times the mass of the wheels plus the mass of the pulley. Okay? And then you can see on these two terms, the R is going to be squared here, and it's going to cancel, right? And this R down here is going to be squared, and so it's going to cancel, okay? And I end up with this. Okay? And then, of course, that means that VF equals 2 mgh over this, all of this stuff, all in a root, okay? And that's it. Now, I made the problem seem like it takes a really long time to explain in detail every step, but it didn't actually take that long to do if I was just doing it in my head and I didn't kind of explain in great detail every step to someone else, right? I just looked at, first I picked an initial and a final position, okay? So maybe I'll erase the picture here. Okay, so in the end, how did I use conservation of mechanical energy? 1, I picked an initial and final position and time. Okay? Position / time. Okay? So I picked an initial and a final state of the system that I cared about. Okay? Which is things are in this kind of place, right? I picked a time that's initial and things are in this place at that time, and I picked a time that's final and things are in this place at the final. Okay? That's the first thing I did. Second, I looked at each term. Okay? And that means each term in this general equation. So I looked at this one, and I know that it can only have either gravitational potential energy or spring potential energy. Okay? I looked at this one. I know that it can only have translational kinetic energy or spinning kinetic energy. Right? I looked at work non-conservative. That's the hardest one. If that one there are non-conservative forces, that's the one where I have to really take some time and figure out exactly what's going on here. And then remember, if it's something like friction or something like that, that term is going to be negative because it's going to be taking energy out of the system. Okay? So if I have to solve for like the effect of kinetic friction or something like that in a conservation of mechanical energy problem, I'm going to want to subtract however much work friction does because it's taking mechanical energy out of the system. Okay? And then again, I did the final potential and the final kinetic, and again, those can only have these possible values, right? These possible expressions. Okay? That was it. I just looked at each term and I just wrote down what was there. Here on the left side, when I'm looking at those terms, I only care about what's there in the initial position, okay? I don't even look at the final position. It doesn't matter, okay? I just write down what's there in the initial position. And here, I just write down what's there in the final position, okay? The only time that I might compare initial to final during this process is for gravitational potential energy, because I'm only going to care about changes in height, okay? So if something has its height change, then it's going to be important. But even if I don't do that, even if I just want to include everything that has gravitational potential energy in my problem, that's fine because it's going to cancel in the end, okay? Because if it doesn't change in height, it's going to have that potential energy at the beginning, and then when you go to do this U final term, it's going to have that potential energy again at the end, okay? They'll be on both sides of the equation, and they'll just cancel, okay? So even if you write down one where the height doesn't change, it'll cancel at the end as long as you keep doing everything correctly, okay? And then 3, okay, after I did step 2, I had this. I had conservation of mechanical energy for the specific problem that I'm looking at, right? I solve algebra, okay? That's it. I just do math from there. I just solve algebra. And then I'll put kind of 3a we'll say extra minor physics. For example, rolling without slipping. Okay? You might need to know something like centripetal acceleration or rolling without slipping or something like that that allows you to kind of replace a variable, right? Just do a substitution in your algebra, okay? But other than that, I'm mostly done with the problem after step 2. Once I have this one, I just have to solve for the thing that I want to know, okay? And that is hopefully helps for any students that were unclear about how you use conservation of mechanical energy, okay? You just follow these steps and you just be really anal about your accounting for everything, okay? You just be really careful, really particular, really pedantic about what's there and what's not, and you just record every little thing. And then when you're done, you step back and you look at this new equation that you've written, which is now not just conservation of mechanical energy in general, but conservation of mechanical energy for your specific problem. Okay? So, like I said, I didn't have slides or anything for this video. I was just thinking about how I intend to make the test, and that I would like to include some conservation of mechanical energy problems on the test. And I just thought that it would be nice for any students that didn't feel totally comfortable with conservation of mechanical energy for me to just grab a couple problems and really just walk through in detail how we apply this tool to solve problems. Okay?